In this video, we'll talk about how to find the length of the shortest path between two nodes in a directed graph. So to start, let's clarify what exactly the question is asking. Let's say, for the sake of example, we have the graph on the left and we are given two nodes. Let's say we're told that our start node is what I will mark in S here, so node 0. And our end node is what I'll mark with an E here, so node 5. We are trying to figure out what is the shortest path from the start node, 0, to the end node of 5. And the way we define a path length is how many edges are in between. So for example, if you're at the 0 node, and then you go to the 1 node, and then you go to the 3 node, and then to the 4 node, and then to the 5 node. This is a valid path, and it took 1, 2, 3, 4 total edges, A, C, D, and F. So that has a path length of 4. If we go this way, you can see if we go from 0 to 2, 0 node to the 2 node, and then the 2 node to the 5 node, taking edges B and E, we only have a path length of 2. So that's actually shorter, and that is the shortest path here. That's not too difficult to see as a human, but doing it in code is not so trivial. So this is a BFS question, which I'm sure you can tell by the fact that it's in the BFS category. But I want to talk about how we know that we should use a BFS here. And the giveaway in this problem is shortest path. Generally, if you want to find the shortest path between two nodes in a graph, there's a very good chance that you can do that using a BFS. And there's a good chance that the optimal solution uses a BFS. That's not always the case, but it is pretty common that if you're trying to find the shortest path between two nodes, the BFS could be a good strategy. And I want to talk about why that is. So a BFS kind of goes level by level. So if we're at the 0 node, we first consider these nodes, then these nodes, and then this node. The reason that's important is because we first consider the 1 node and the 2 node, right? These two, which both have a distance of 1. Then we consider, if we are at the 1 node and the 2 node, we say, all right, from the 1 node, go one step further and grab this 3 node. From the 2 node, go one step further and grab the 5 node. So we grab these two. So we can write that for the 1 and 2 node, the distance is equal to 1. And when I say distance, I mean distance from the start node. So distance equals 1. I'm going to go ahead and abbreviate distance as D for simplicity. So here we can say D equals 2. Let me do that. Let me do it here. Distance is equal to 2. And then at this last sort of level that we're going to go through, this level only has 1 node, but it's still a level. The distance is 3. So you can see that the nodes that are the closest to the start node, we attack first, right? We do the 1 node and the 2 node before we do anything else. Then we attack the 3 node and the 5 node, right? So we're kind of going in order of how far these nodes are from our start node. This is important because it really helps with finding the shortest path. The reason is because when we hit the 5 node, we know that 0 to 2 to 5 is our shortest path because it has two edges of B and E. Now, the way we find that using a BFS is we start at the 0 node and we BFS over, through our BFS as we traverse the graph. We go to the 1 node. We check, hey, is this our end node? No, it's not. Then we go to the 2 node and we say, hey, is this our end node? No, it's not. So then we know it is not possible that we get a distance of 1 as our answer. Our distance must be something that is greater than 1. So it should be 2 or larger. Then we go to the next level and we go to the 3 node and we say, hey, is that our end node of 5? No, it's not. So we move on. We go to our 5 node and we say, hey, is this our end node of 5? And it is. And now we already know the shortest path, the length of the shortest path. It's 2. The reason is because we are going from smallest distance upwards, which means we know that there is no value smaller than 2 that allows us to get to the 5 node. Because if there was some way we could have distance equals 1 and find the 5 node, we would have found it when we looked at distance equals 1 here. But we have already checked every node where the distance is 1, and none of them gave us the 5 node, which means 2 is the smallest value possible. It's possible there are other paths to the 5 node if we continue searching onwards. And there are. We could go from the 3 node to the 4 node to the 5 node, but those will have distances that are greater than 2. So because of the fact that we first search the nodes of distance 1, then distance 2, then distance 3, and so on, the first time we find our end node, we already know the answer and we don't have to do any more searching. Okay, so that's the core idea. We're going to BFS through our graph, and the second we find our end node, we want to return the length right there. Now, one point I want to make is we actually need to store these distance values, because how do we know that 2 is the number we return? Like, just if we do a normal BFS, we won't know that we are a distance of 2 from the 0 node. So the way we're going to do this is in our BFS queue, we will not only store the nodes themselves, but we'll also store their distance from the start node. So I'll do that on the top left corner. Let's do it. Yeah, we'll do it on the top left corner. So as an example, on the 0 node, the distance from the 0 node to the 0 node is just 0, right? It's already at itself. These two nodes have a distance of 1. These two nodes have a distance of 2. And then this node has a distance of 3, all relative to the start node. So what we'll do is we'll put those values into our queue. Now, this is something that's slightly different from what we're familiar with. The way we've handled the BFS so far is we just put the nodes into the queue. But now we have to put 2 pieces of information at a time into the queue, which is a little bit different. And this is a very common pattern, which is why I'm showing it here. And there are several ways you can do it. You can use an array. So every element of your queue would be an array, in our case containing a node along with its distance from the start. You could also use a hash map. So every element of your queue would be a hash map. Or you could build a class, so that you can create an instance of that class, like an object, that contains the distance and the node. Any of these methods work. It just really changes what is the data type inside of your queue, but it doesn't matter too much. Okay, so let's go ahead and actually write out the pseudocode for how this solution is going to work. So we know we're doing a BFS. So the very first thing we'll do is we are going to add the start node to the queue. And we want not only the start node, but we want its its distance to be in the queue. So that's the 0 value right here. Yeah, that's fine. Yeah, to our queue. To our queue. That's the very first step. Then we want to, in standard BFS fashion, we'll say while the queue is not empty. So while queue is not empty, what do we want to do? Well, there are 3 steps to a BFS. We remove a node, process that node, and then add neighbors or children to the queue. So number 1, we want to remove the node and its distance here. So remove node and distance. I'm going to skip the process part for a minute. We'll come back to that. And then we'll add children. This is pretty straightforward. We've seen this before. It's not very exciting, so we'll just say add children. And yeah. And one thing to note is we have to provide the distance for the child. So it'll look something like this. It'll be child and then dist plus 1. I'll explain this in a moment. Okay, I want to come back to this process step. So if you remember from previous videos, the process step is basically what logic do we want to apply to every single node that we touch. And the question I asked as we were going through this was, is the current node our end node? Right? And when we hit it, we just returned 2. When we had our current node was the 5 node and our end node was the 5 node, we just returned its current distance. So what we're going to say here is if current is equal to end, so current node equals end node. By the way, I should have mentioned up here that in the input, we'll also be told what the start and end nodes are. I forgot to include that, but it's not a huge deal. They're marked on the graph. Okay, so if the current is identical to the end, what do? We return the distance. And when I say distance, I mean I'm just talking about the value we grab right here. So this covers the logic. The idea is the first time we ever find the end node, we know we found the shortest path because BFS goes level by level. Now the question becomes, why are we adding the child and then dist plus 1 to the queue? Well, we discussed that every element of the queue needs to contain two pieces of information. The first is the node, and the second is that node's distance from the start node. Now, the node itself is not too difficult to explain. That's just how you do a BFS. But why is the distance equal to dist plus 1? Well, think about it this way. If we are at the 2 node right here, we know the 2 node has a distance of 1, and we want to add this 5 node to the queue. Well, we know the path from the 0 node to the 2 node is of length 1. And if we want to get from the 0 node to the 5 node, what is the distance going to be? Well, all we have to do is just go to the 2 node and take one extra edge. So the distance to the 5 node is the exact same thing as the distance to the 2 node, except we have to account for this extra edge here, e. And this is generally true, where the distance to a particular node plus 1 gives us the distance to all of its children. So when we're adding a child to the queue, the child's distance is equal to the current node's distance plus 1. Okay, so that is the core of how our BFS algorithm looks in terms of pseudocode. I do want to highlight a particular pattern, which is the fact that we're storing two pieces of information here. And I did this as an array for the pseudocode. It doesn't necessarily have to be done that way in code. But this idea of storing multiple pieces of information at each element in your queue is very important because it shows up fairly frequently when you're working with these BFS problems, and it's an important idea to be comfortable with. So it may not be something that you'd immediately think of, and that's totally fine. It's something that comes with exposure and practice. But do understand that this is an option in your tool belt that you may use on a particular problem. Okay, so let's go ahead and break down the complexity of this solution now. It's not going to be crazy different from what we've seen before, but I think it's worth it to do regardless. So before we actually do that, let's define our variables. So we know v is going to be the number of vertices in our graph. And then e is going to be the number of edges in our graph. Okay. Now our time complexity is going to be O of v plus e. We've seen that before. And our space complexity is going to be O of v. Now, this is mainly determined by our BFS. So in terms of the time complexity, the v comes from the fact that every node in the worst case scenario is going to be added to the queue at some point. Because there are a total of v nodes, and adding to the queue is constant time. So that's where the v comes from. In terms of the number of edges, well, for every node, we're exploring all of the edges on that node in the worst case. If you do that for every node, then in total, you're going through every single edge in the graph. So that's where the e comes from. It's not per iteration, but it's overall. So we do v plus e as the time. In terms of the space, in the worst case scenario, you can imagine if we had a graph that looked like this, where we have our central node, and then a bunch of different other nodes. And this is a directed graph, so you can imagine these are arrows pointing outward from the central node. Well, when we process this central node, we're going to add all of its children. So we're going to add all of these nodes onto our queue. So at that point in time, we're going to have, our queue will contain every node in the graph except the central node. So there are v minus 1 nodes in the graph. So in the worst case scenario, our queue has v minus 1 nodes. So that's O of v space overall. That's all for the approach. So let's go ahead and switch over to the implementation. Now, let's see an example of how to solve this question in JavaScript. To get us started, I have three things. I have our queue that we'll use in our BFS. I have our inputs, which are an array of edges, a 2D array, our start node, and our end node. Our output is the length of the shortest path between our start node and our end node, which is 2. Okay, so the very first thing we'll do here is we'll write out our test. So let's say our edges is going to be these edges here. Our start node is going to be 0. Our end node is going to be 5. What we want to do is just print out length of, let's do get length of shortest path, and we'll pass in edges, start node, end node here. Okay, so we have that. Now let's write out that function where all the interesting logic happens. So we're going to take edges, a start node, an end node. That's all. All right, so we know by now the first thing you do when you get edges like this is you want to create a graph out of them, as in an object in JavaScript. So let's say our graph is going to be build graph, passing in those edges. We can come over here and write our build graph function, and we're going to take some edges, and we know how this works by now. We're going to create a graph, which is an empty object, and we'll return it in the end. Oops. In between, we want to iterate over our edges. So for each, take an edge. And what do we do with that edge? Well, we want to grab out the two nodes from it. So we'll say start and end is going to be edge. Then we'll say graph at start dot push end. But before we do that, we have to make sure that there is an array to push into. So we'll say if not graph at start, then graph at start should just be an empty array. All right, fantastic. So now we have our graph here. The next thing we want to do is actually conduct our BFS. So what we determined is we're going to BFS outwards from the start node until we hit a point where we find our end node, and at that point we want to return the distance. So we'll have our queue, which we will definitely need, and we want to put something onto our queue to get started. Now remember, we aren't just storing nodes in our queue. We're storing two pieces of information, a node and its distance. So, like I mentioned, there are several ways to do this. You can use an array, you can use an object in JavaScript, or you can use a class. And whichever you use, those would be the elements of your queue. I am going to use a class here. So I'm going to call this node distance pair. And I want to be clear that you don't need to use a class. There are, like I said, several ways to do it. Hold on, value and let's say dist from start. Okay, yeah, there are several ways to do it. You don't have to do it this way. It's completely fine to do it with an array or an object. I'm choosing to do it this way for this question because I want to show the fact that you can use a class like this, because in some problems you're storing more than just two pieces of information, and trying to use an array or an object starts to get ugly. Whereas using a class is a little bit more scalable, meaning that you can store, infinite properties. I mean, not literally infinite, but you can store a lot of properties on each object. So let's actually change this to node. So our class is going to store two pieces of information. It's going to store the node, and it's going to store the distance of that node from the start. So we have our constructor that takes in those two arguments, and we don't need anything else. All right, so every element of our queue is going to be an instance of this node distance pair class. So what we do, let's do this. So let's say initial node pair is going to be a new instance of our class. And then we need to pass in the node, which will just be the start node. And its distance, well, it's going to be 0, right? Because the distance of the start node from the start node is 0 because it already is the start node. So this may look a little bit different from what you're used to, but really it's the same idea of what we already know how to do. We're just putting the initial node into the queue. The only difference is now we don't just want the node, we want a little bit more than that. Okay, so now we have the same BFS condition, which is just so long as anything is in our queue. And then we do what we've learned how to do, right? We want to there are 3 steps. We remove a node from the queue, process that node, and add its children to the queue. So first, we want to grab a node from the queue. So we're going to do queue.dequeue here. Now keep in mind, we are not just getting the node here though. This is actually the entire node distance pair. So we can rename it to node distance pair, and we can destructure out what we care about. So we care about the node and the distance from the start. So we'll say, all right, grab out the node and distance from the start from our node distance pair. This is just a little bit more, work that we're doing in terms of how we remove information from the queue. Okay, so now we have our information. For a second, I'm going to skip the step where we process the node, and let's talk about how do we add children of this node to the queue. Well, the first thing we need to do is get all the children of this node. And how do we do that? Well, this is what we built our graph for. Our graph allows us to map from a node to every node that we can access from the current node. So we can just say the children is just going to be graph at the node. This gives us all of the children that we need to worry about. And then we have our standard edge case, which is like, hey, if there are no children, if children is undefined, and the node's not even a key in our graph, then you want to just continue. Otherwise, we want to iterate through each child. So we'll say, all right, take each child. And what do we want to do? Well, it's not as simple as just adding them to the queue, because remember, we can only add node distance pairs to the queue. So we actually need to get the distance here. So what we're going to do is we're going to say new, let's say child distance pair is going to be a new node distance pair, and we need to pass 2 arguments. The first is the node, which is just a child, and then the distance we discussed in our approach is going to be the current distance, like the distance of the current node, plus 1. Because to get to this child, what we have to do is get to this node up here. So we use a distance of start to get there, distance from start, and then we have to take one more edge to get to the child. So this is going to be distance from start plus 1. Now we've created our child distance pair, so we need to add that to the queue. So we'll say queue.enqueue child distance pair. Okay, great. So now we have our standard BFS boilerplate code set up. Right, we're pulling out nodes from the queue, we're adding nodes to the queue. The only question becomes, what do we want to do for each node? Right? This is the process step. For every node I want to do X. And if you remember in the approach, the question we asked for every node was, hey, is this the current node? And if so, we want to return the current distance. So this is just going to be, if the current node is equal to the end node, all we have to do right there is just return distance from start, and we're done. Right? Because we have found, so we would have found our end node, and because we're using a BFS, we know that this is the shortest path to the end node, so we can just return its distance from the start. Now, if we want, there is probably a weird scenario where we never hit this return statement because we aren't able to find the end node. So what we can do is, in that case, I'm going to return -1. Because we know -1 will never be a valid answer in terms of the length of the shortest path. So I just kind of want to signify, like, hey, something went wrong here. The end node should have definitely been in our graph, and it should be reachable by the start node. This means it's not reachable by the start node, or it's just not present in our graph. Okay, great. So that covers the core of the solution. Let's go ahead and test it out. So, let's see. So we can, so we wrote our test. So we know that the expected output is 2. So we can come here, we can quickly do node length, and we should get 2. Okay, fantastic. It looks like that works. Now, I want to highlight a common pattern that can be clearly seen in this problem one more time. This idea of how we're storing multiple pieces of information at every element in our queue. So every element of our queue, we only add to our queue in 2 places, right here and right here. Every time we add to a queue, you can clearly see that we are not adding a node. We're adding a node distance pair, which contains a node and a distance from start. This is important, and there are many ways to do it, but this can be used to solve a lot of different problems. So if you understand conceptually this idea that sometimes we don't just want to store a node, but rather we also want to store some extra information with that node, that will be very powerful in future problems. Okay, so that is the main solution. Let's talk about the time and space complexity. So we'll start by defining our variables. So we know that V is the number of vertices in our graph. E is going to be the number of edges in our graph. And we can say our time complexity is going to be O of V plus E, and our space complexity is going to be O of V. Okay, so the time complexity is the V comes from the fact that every node would be put into our queue in the worst case scenario. So that's every node is, nodes and vertices are the same thing, so that's O of V. And every edge in the graph will be explored at some point in time in the absolute worst case scenario. So we have V plus E for the time. For the space complexity, we have the worst case scenario where you have a central node and everything else just comes out of that central node. In that case, you would have V minus 1 nodes in the queue at one point in time, so you get an overall space complexity of O of V. That's all for this video, and I'll see you in the next one.